What happens to the value of sin x, divided by x as x inches closer and closer to infinity? A question that may seem daunting at first, but with a little bit of mathematical finesse, we can tackle this head-on. Let's embark on this journey by understanding two key elements: the sine function and the denominator, x. You see, the sine function or sin x always dances between -1 and +1, no matter how colossal or minuscule x may be. This behavior of the sine function is what we call bounded. On the other hand, our denominator, x, isn't quite as well behaved. As x approaches positive or negative infinity, it grows without any bounds. This discrepancy in behavior between the sine function and x sets the stage for our next step, applying the squeeze theorem. Now imagine two functions, gx equals -1 over x and x equals 1 over x. As x approaches infinity, both gx and hx inch closer and closer towards 0. And here's the kicker. For all real values of x, our original function, sin x over x, is squeezed right between gx and hx. This is where the squeeze theorem comes into play. According to this theorem, if a function is sandwiched between two other functions that converge to the same limit as x approaches a certain value, then the squeeze function must also converge to that same limit. So what does this mean for our function sin x over x? Well, since it's squeezed between gx and hx that both converge to 0 as x approaches infinity, it too must converge to 0. In conclusion, the limit of sin plus x divided by x as x approaches both positive and negative infinity is indeed 0. This analysis not only resolves our initial query, but it also showcases the power of the squeeze theorem and how it can be used to analyze similar limits involving bounded functions divided by unbounded ones. So, the next time you encounter a tricky limit, remember, a little squeeze can go a long way.